Okay, so we are looking at number 7 on the Unit 2 practice problems. The problem says the population of a city in thousands can be modeled by the function p of t equals 328 times 0.9917 to the t, where t is the number of years after July 1st, 2000. And we got a whole bunch of questions about this model. Let me point out a couple of things about this model before we even get into the questions. And I think it's always a good idea to think about the problem before you just dive into the questions, if you have the time to. Specifically, what I want to point out is that this is a decay model. So this model is actually decaying. I know that because this number is less than 1. All right, so with that in mind, let's move on to the questions. So first, find this population's annual percent growth rate. Okay, so I know, because it's a decay model, that the growth rate will be negative. So I should have a negative answer here. Keep that in mind. So how do we get the growth rate? Well, we take the factor, which is 0.9917, and we subtract 1 from that factor. Basically, we do this. Oops, sorry. And so b equals r plus 1, therefore r equals b minus 1. That's the relevant equation right there. R equals b minus 1. So let me go to the calculator, and we'll do this. So that's 0.9917 minus 1. And then we will need to put that in percent form, but multiplying that by 100 gives me negative 0.83%. So as expected, we have a negative growth rate, and that's it, negative 0.83%. Okay, how does the population change over time? Well, it's a decreasing function, so it's decreasing exponentially. That's how it changes. Question C, find the per decade decay factor round to 4 decimal places. And let me go ahead and look at question D also, find the per decade percent decay rate. So both C and D have to do with changing the time unit from annual to decade, but notice that one is about the factor and one is about the rate. So I think a lot of times people miss these factor questions because they see that and they automatically they go too far and find the rate, but we're actually going to find both of them here. Okay, so I'm going to bring up my whiteboard. My annual factor is 0.9917. That's just from the problem. So the first thing that I do is raise that to the 10th power. Now that is the factor. This is the decade factor. So this will be my answer to the part C. So let's find it. And so it's 9200, and this is not a percent or anything, okay? So I think a lot of times when people do these factor questions, they put a percent sign after it or try to subtract from 1 or something like that. But this is the answer, 0.9200, no percent, that's it, okay? Now the per decade percent decay rate, to get that, if I subtract 1 from the factor, what I have now is the per decade growth rate. Now I want the per decade decay rate, so in this case I do actually change the sign because it's explicitly asking for the decay rate, which is positive. So it has a positive decay rate because it is actually decaying. So I need to change the sign of this, but I also have to convert it to percent form, and That's because this is a rate, not a factor. So our final answer, if we round this, well, this is going to round up to like 8.0, but is going to be 8 point, if we're going to say 2 decimal places, that would be 8.00%. Okay. What about the average rate of change in the interval 0 to 5? Well, to do that, we have to do some computations. And there's a couple of ways you can do this. You can program this in using delta list, or you can just compute it. Since it's only one function, it might be just as easy just to compute the function directly, or the average rate of change directly, rather than doing delta list. So I think that's what I'll do. So I've got my function entered, and I'm going to do y1 of 5. So basically I'm going to do the numerator of the average rate of change here. And then my denominator, so there's my numerator, and then I'm going to divide that. It's just 5 minus 0. So that's 5, but that's my denominator. And there is our average rate of change, negative 2.68. Okay, there is a negative sign there. Okay, moving along. The city's actual population on July 1st was 326.4. Find the model error. And then for question G, it's the same question. It's just that there it's going to be asking for the model percent error. So the model error is actual minus predicted. So this is the actual value, 326.4. And then the predicted value is going to be the value of the function at that time, which is I think actually there might be a mistake in this problem. I'm going to pause the video and try to sort that out. Okay, so in regards to number F and G, there's no mistake. That was I was thinking that perhaps 2000 was that was supposed to be something else, but it's not. So July 1st, 2000, that's when we actually started the model. So in any case, so calculate the model error. So as I was saying, that's the actual value minus the predicted value, and the predicted value is, in this case, just going to be y1 at 0. And I see that I entered the value wrong. I'm sorry about that. 300 and let's do that one more time and try to not make any mistakes this time. So y1 of 0. Okay, there we go. So there's our model error. Now to get the model percent error, the formula for that is the model error divided by the actual value times 100. So I just need to take this and divide it by the actual value, which is 326.4, and then multiply that by 100. And there's our percent error, negative 0.49%. For part H, predict the population of the city on July 1st, 2015. That's 5 years in the future. So we just are evaluating the function after 5 years. And we get 314.61 thousand people. And finally, to find the year in which the population will reach 300,000, this is a calc intersect question. So y2 will be 300. I'm going to go to the table and find my intersection. I happen to be at 16, which actually is too far, so I need to go back because I already passed 300. You see, that actually happened right here between 10 and 11. So my window could be from 0 to 15 would be plenty. And then we'll do zoom fit. And hopefully we'll see our intersection point here. There it is. And so that is 10.71 years. Now, if we started in July 1st, 2000, that would be July 1st, 2010, but 0.71 is greater than 0.5, so that would be more than half a year. So this would be 2011 would be our year. All right, let's look at number 8. A country collected $490 billion in taxes in 2016, and its tax revenue is increasing by 2% per year. The same country spent $760 billion in 2016, and its expenditures are decreasing by $15 per year. Assume these trends continue. So it's important to realize that we actually have two different models at work here, and we're going to be letting those two models interact. So let's sort them out. We have an expenditure and a revenue model. The revenue model is given in terms of a rate increase, a percent increase. So that's going to be exponential. Whereas the expenditure model is given in terms of a constant per year decrease. So every year we lose the same amount. That is a slope. So that's going to be linear. So we have an exponential and a linear model to work with here. So we're going to use both of them. I'm going to program these directly into the calculator. So Y1 will be my revenue model. That's the exponential model. So it's going to look like this. 490, and then I have a 2% rate, so that means my 1 plus R is 1.02, and that's raised to the X power, so that's my expenditure model. I'm sorry, my revenue model. And then my expenditure model is going to be the linear function, so we can use mx plus b for this. So m is negative 15. And then my intercept, my y-intercept value is 760. Okay, so those are my two models. And I'm going to have to evaluate each of them. So for question A, it says what are the expenditures in 2019? What is the revenue in 2019? So expenditure is Y2. So that's going to be evaluating Y2 at 3, right? Because 2019 is 3 years in the future. So 715 is our expenditure. And then for our revenue in 2019, we're going to do the same thing, but we'll use Y1 for that. And our revenue is 519. And then for question C, when will be the first year when the country's budget is balanced? For that one, I'm going to go to the table and look for, actually, let me go back to time 0. And what we're looking for is for column, notice that column Y1 is increasing, column Y2 is decreasing, so we're looking for the point when these two pass one another. So let's kind of carefully scroll through here and see when that happens. Okay, so it's getting close now, and I think there we go. Okay, so it just happened. Do you see that? Y1 now is larger than Y2, so we need to go up to 10 or 11. So I'm going to let my window is at 15 right now. That's